Today, it's February 5th, 2015. I'm Paul McJones in California,
and
I'm interviewing.
I'm Bjarne Stroustrup in New York City.
And behind the camera is John Plute. How are you, Bjarne?
Fine, thanks. Thanks for taking the effort here. And it's amazing we can sit chatting like this.
Yeah, several thousand miles apart. We're using probably some C++ technology behind the scenes.
Definitely, and I was thinking that when I started on this, we couldn't have done this.
Right. I thought it would be good to sort of start at the beginning if you could tell us a little bit about your parents, where you grew up.
Okay, yeah. I was born in Aarhus in Denmark, and I lived there for the first sort of 23 years of my life. Lived in an apartment in a working class district. My father was somebody who laid down floors, and later after an illness he was a hospital porter. My mother was a secretary. So she has had a middle school education, which was the most anybody in the family had by then. So I went to the local school, which wasn't a great school. Actually, I've seen the statistic, it was the worst school in town. But somehow I managed to get into high school, and from there to the local university. And that happens to be a good one. University of Aarhus sort of appears on the top 100 universities in the world ever so frequently. Not every year, but lots of years. And I actually had a pretty nice time in Aarhus growing up, and a very stable situation. We lived in one place, known as the Yard, some of those standard rectangular apartment buildings that you got in Europe, with a yard in the middle with some grass and such. Very nice place. I've traveled far and lived in other places, but it's not because I disliked where I came from. I've still got family in Denmark. I studied mathematics with computer science in the university, and that's actually curious because like most high school students, I hadn't a clue what I wanted to do. So I was looking around. I wanted to be a historian, an architect, a sociologist, an engineer, and decided I didn't know. So I just got grades that were sufficient to get into anywhere. And so I was thinking of going to the engineering school in Engineering University in Copenhagen, but decided that the costs were too high. In Denmark, of course, you have free tuition, so that's not a problem. But coming from a family with few resources, the idea of taking on debt for a 6-year course living in a big bad city, meaning Copenhagen, was just too much. So I decided I'll do something local. And since we didn't have an engineering school, and since I had been reasonably good at math in high school, I signed up for math. But I was convinced that I needed to do some practical math. I wanted to actually practice something, to do something. I had an absolute dread of becoming a teacher, because I thought that was what happens to bright kids who don't know what they're doing. Have no role models, have no ideas what they're doing. So I didn't want to be a teacher. So I needed to find some kind of applied math, something I could really do. And so I signed up for computer science. The word computer is not in the title of that in Danish. So I was quite capable of misunderstanding it and thinking it was math. And in my second year, I realized that I'd been wrong, and programming, data structures, machine architectures is not math. At least not at that level. And this was pretty good, because it turns out, like most other people, I wasn't quite as good at math as I thought I was. On the other hand, programming was really fun, and learning about machines and computer science in general was really fun, and haven't looked back since.
Well, that's pretty interesting. Were there any sort of mentors or anybody who had influenced you down this path up to this point?
Not in any sort of real sense. I've thought about this problem before, and I did have a math teacher for actually 9 years running, who was a very good math teacher. So that's probably why I didn't flunk math, and I actually was reasonably good at it. But he himself had been trained as a Danish teacher and had never actually been to a high school. He'd been from middle school to a teacher's training college, and he couldn't guide me beyond that. And nobody in my family could, so once I was in high school I was sort of on my own, and with a bit of luck I ended up in that computer science program and got my master's in mathematics with computer science. Never regretted the amount of pure math I ended up doing. You never know what comes in handy in your career, and if you told me, say 20 years ago, that algebra turned out to be a really useful thing, I would probably have argued strenuously against it. But with type theory and Alex's work on the STL and that kind of stuff, the kind of thinking I learned in algebra has actually been very useful over the last couple of decades, after being not useful at all for a couple of decades.
Right, but it was sort of latent in there.
It was there.
Do you remember? Pardon?
It was there.
Right. Do you remember, particular textbooks that seemed, important to you at the time?
What pops into my head is a book on the opening game of chess. I don't think that counts. No, I don't think. Greece's book on how to write a compiler, very practical. The only problem was it was mostly grammar errors, and when it came to real design, it was the least important part of the compiler. But it got me started and interested in languages and how to implement languages. I was never a languages guy. I was interested in operating systems. I dealt with microprogramming a lot, machine architecture. One of my early projects in Aarhus was to design a virtual machine in hardware for BCPL. I needed to run BCPL, or rather I wanted to run BCPL, and I looked at O code, which is basically assembly code for BCPL, and thought, well, why don't I just implement that in hardware? So I wrote a little piece of microcode that implemented an instruction for instruction. I made a little representation of O code with compressed data structures so that you could have a compact program, and now I could run BCPL. So this is not quite the traditional way of implementing a programming language, but Martin Richards had kindly provided this intermediate step in the compiler, which I could hijack. And I learned probably a dozen, maybe 20 languages before I left Aarhus. I got a master's. That's what you got in those days. There was no bachelor's. So I was not a languages guy, but I did know, say, 20 languages.
So that probably included the sort of the applied ones like Fortran and so on.
We have...
Hold on for 1 second, I'm making a slight adjustment. Can you see him okay, Paul?
Yes, everything's good.
Okay, hold on. Checking focus. Okay, go ahead.
I was just curious, having learned that many different languages, did that include sort of practical ones and also some of the research languages?
The distinction between practical and research languages was never explained to me, and I don't think I appreciated it. The first course I think had 3 or 4 languages. I remember writing some COBOL and hating it, writing some, lots of languages, and some of them I liked, some of them I didn't like. When I say 20 languages, it doesn't mean I have completed a major project in each, but it means you've written a couple of programs, you appreciated what it can do and what it cannot do. What is that string manipulation pattern matching language from the 60s?
Snowball?
Snowball, that's right. I remember finding Snowball really interesting and useful. And one, what I would call formative experience, was realizing that I had written an algol program in Snowball. And it was a really stupid program. It was complicated, it was difficult to get to run, it ran slowly, and it was not how any sane Snowball programmer would write it. And so you had to go back and actually learn the idioms. You can't just take a language and start writing it as if it was your previous language, which is what we essentially all do. And then we realize we're doing it again and correct. But that I actually learned, I think, in the first half year of programming. And so I picked up quite a few programming languages. I mean, you can pick on, in the old days when languages were simpler, programming environments were less complicated, libraries was less extensive, you could actually find yourself sitting waiting for a couple of hours and then read the manual and go back and write some programs when you got out of the waiting room or wherever it was you were stuck. And then you could play with it for a couple of weeks or a couple of months, do something it was suitable for, and get on with something else. But languages were never my main concern. Languages was a tool for doing something, like for getting hardware to do the right thing, or getting hardware to have the right instruction set, or something like that.
Right, right. In Steve Lohr's book, Go To, he mentioned that you were a contract programmer at that time. Did that have a strong influence on you?
It did. It wasn't meant to, it was just meant to give me some cash so that I could avoid taking on debt and live frugally but reasonably up to my master's degree. Some of the microprogramming again was done on contract from the university. But this job from Burroughs was actually interesting because there I got to see the process from negotiating with the client what should be done to deciding what could be done out of what the salesman wanted and what the client wanted, and then building a demo. And I had a very simple business model. If I could build a demo that the client was willing to pay for, then I got the job of implementing the system. Now, this, from the corporation's point of view, is safe, because if I sell a demo I cannot make real, I wouldn't be working for them anymore. On the other hand, it is very much in their interest and the client's interest and my interest to get the system as nice as possible. And I was out talking to the clients, also talking to them when they were installing it, seeing how it could install, see how to train the people who's actually going to use it, sit around chatting with the client's children, realizing that if I screw up, these children get hurt. So as I thought about it, as I went along, I did this many times, between 6 or a dozen times over a few years. And then I thought about it later, and I'd actually seen the whole process of software development, from trying to figure out what system might get built to doing the cleanup once something broke, and everything in between. And I have a fairly strong opinion about systems being appropriate and reliable and affordable, which I think partly came out of that. It is not something that is easily installed in a classroom setting.
Right. It kind of reinforced those feelings you had initially that you wanted to go into an applied field, but it really made it concrete.
Doing something practical and sitting there on the sofa trying to explain to a couple of kids what I'm doing for their dad is an interesting exercise.
Yeah. Okay, so at that point you could have gone probably easily started some sort of a software development career, but instead apparently you decided to go to graduate school. What led to that?
Yeah, I actually got to England before I got my master's because I was working with some microprogrammable hardware and they had some really cool stuff in England. So I went over there for a while, and while over there I got the idea that actually was interesting and I could do something more. And getting a PhD was my solution to the problem of how to spend more time in England and play with some more interesting hardware. And so I applied to sort of the English universities I'd heard of and actually managed to get accepted in most of them. And I was almost going to Newcastle, but my wife, my then girlfriend, explained to me that if you have an offer from Cambridge, you take it. This is non-negotiable if you're in England, and I haven't regretted that. It turned out to be right. It's probably still, for practical computer science, the best place in Europe.
Yeah, it certainly seems to have turned out well for you. And your advisor was David Wheeler, and his advisor was Morris Wilks. And these were the people who got the first practical computer running. So
yeah,
it really connected you to the origins.
And it turned out that Wilks was the guy that invented microprogramming. I mean, would you believe it? I sat in an interview with Roger Needham and Morris Wilks at Cambridge, and I somehow hadn't dawned on me that Wilks was the one that invented microprogramming. And so I was explaining all the cool stuff about that without knowing who I was doing it to. But I must have done a good job because I got accepted.
Yeah.
But that was the toughest interview I've ever sat through. There was these two guys. I mean, Wilks got the second Turing Award. He's no slouch. And a computer museum history fellow, by the way. I'm a third generation here because later Wheeler got it and now I'm getting it. And there was Roger Needham, who later became Vice Chancellor of the university and started the Microsoft in Europe there. And so they were taking turns. One of them asks a question, the other one listens. And when we run out of that question, the other guy asked a question. And I don't think I've had as hard 3/4 of an hour ever as that interview. Halfway through, they explained to me that I was all wrong. And was there anything else I could do? So I had to change horses in the middle of that interview. But that was interesting. I remember it fairly well.
Yeah, that sounds pretty tense. But then you probably got to know them a lot better. You have sort of say 2 years later, how did you look at them?
Yeah, the sort of teaching style at Cambridge was somewhat different than most people think. I had a master's when I came in, so I didn't actually need to take any courses. I took courses when I needed them. And David Wheeler's tuition style was very simple. You came to him when you thought it was a good idea, and I quickly found that turning up about once a week was a good frequency. And you come in, a new grad student, you're full of great ideas, right? You come in and you're explaining these great ideas to David Wheeler. And he sits there and he sits thoughtfully. Yeah, Yeah, Bjarne, that's not a bad idea. You know, we almost did that for the ETSAC 2, which was the most dreaded words, because that means that in about 56, about the time I entered primary schools, they've thought of it. And then he could go on for about an hour explaining what they did instead and why they did it instead and what the trade-offs were and why what they were going to do instead didn't quite work and how they fixed it again. And so basically the tuition style was to listen to what I said, then shoot it full of holes, ever so politely, and then just giving an impromptu lecture for about an hour on topics related to it. And then I was going away feeling about this big, and then you come back next week for the same. I also talked a lot with Roger Needham, who was one of the senior lecturers at Cambridge. Wheeler and Needham both got promoted professor when Wilkes retired to go to the US to become a consultant for a decade or so. But anyway, he sort of was more sort of chummy with the students. We used to go to lunch with a group of students where he amazingly was able to drink 2 pints of Abbott, which none of us would have been able to do and still work in the afternoon. And his style was different. You want to talk to him, talk about something specific, and he walks up and down talking. And this is more two-way than it was with Wheeler, but he walks up and down. So I develop a technique standing roughly on a corner and seeing him walk like that, because otherwise I'd get really tired just to keep up with him. And he had lots and lots of good and interesting ideas. But most of what I learned in Cambridge was from talking to these two guys that way. I didn't see much to Maurice Wilkes while I was at Cambridge. He was sort of the professor sitting in his office. You had to book a time with his secretary, and if you were a lowly grad student, he probably was busy most of the time. I got to know him reasonably well later, after I graduated. I hosted him at Bell Labs and things like that, met him at conferences. Really, really great guy. He managed to outlive his own autobiography by about 12 years. But one of the things that Cambridge could do, and later Bell Labs can do, is somehow raise people's expectations of themselves. Raise the level that is considered acceptable. You walk in and you see what people are doing, you see how people are doing, you see how apparently easily they do it, and you see how nice they are while doing it, and you realize, I better sharpen up my game. This is something where you just have to get better, because what is acceptable has changed. And some organizations can do that, and well, most can't to that extent. And I've just been very, very lucky to be in a couple of places that actually can increase your level of ambition, in some sense, level of what is a good standard.
That's very interesting. So this is the environment where you pick a research topic, and which is really distributed computing. It's not programming languages, but
yeah,
you have an experience carrying out that research that seems to kind of plant a seed for you.
Yes. One of the first things that happened to me, probably the first day at Cambridge, I was sitting down in Wheeler's office, and he asked me, you know what's the difference between a master's and a PhD? I said, no. He says, if I have to tell you what to do, it's a master's. In other words, it was my job to figure out what to do. That was the first and most important job of a PhD, and it took me a year. The next thing was that he had forgotten that I had a master's. So he explained that the fate worse than death was to get a master's from Cambridge. And I was able to sit there waiting till he'd finished and says, well, I don't need a master's, I've got one. So that was good. But yeah, I had to find the area. The distributed systems came because of my work with machine architectures and microprogramming. I was trying to develop a high-level architecture, architectural support for basically modularity, for having hardware-protected entities talk to each other. In Cambridge, they had the CAB machine designed by Wilkes and Wheeler and Needham, which had hardware protection capabilities. And I wanted to extend this so that it could be on several processors in a single machine, and even better, if I could, on several computers over a network. And the idea was to build hardware that could do that efficiently. And since I couldn't afford a multi-core, I mean, there was hardly any of them on Earth at the time, and I certainly couldn't afford a network. They built the first in Cambridge while I was there, but when I started there wasn't such a thing. So I simulated it instead. And so I was still focused on the systems issues, on the hardware issues, system software issues. And I got into simulation. I picked up the knowledge I had of Simula. I had learned Simula in Aarhus, actually mostly from talking to Christian Nygaard. Many discussions with Christian Nygaard. You don't actually have a discussion with Christian Nygaard. You say something and he talks to you for a while. But great guy, and I learned a lot. So I picked up Simula and I wrote a simulator, and I brought the university mainframe to its knees before I could get any decent data out of it. The resource demands of that simulator was just too much for the mainframe. And later I came to realize that this is typical for simulations. You just run a simulation with more data or with more entities or for longer time till you run out of memory and CPU available. So this is fine, but when you do this as a grad student, you only do it about once before you're kicked off the machine, because the astrophysicists and the chemists have much better funding, financing, and political power. So I had to do something else. And what I did was I moved to actually the CAB, which was this capability machine, very unusual machine, strange architecture, beautiful. You could program it in languages nobody's ever heard of. And that kept the chemists and the astrophysicists and most of the computer scientists away. But I had a choice between Algol 68C, which is Algol 68 without garbage collection, and BCPL. And I did a few experiments. I picked up both of those languages along the way, and I was actually pretty good at BCPL at the time, having implemented it in hardware. So I rewrote my simulator from Simula into BCPL, and all the high-level structure disappeared. All the nice organization that had helped me debug and helped me design disappeared. But the resulting BCPL, once I had debugged it and lost half of my hair in the process, ran really fast. It could use all the resources of the machine. It could communicate with anything on the machine. And I got my data and I got my PhD, and I came away with the opinion that I would never again want to attack a problem with tools that was fundamentally unsuitable. And in particular, I don't want to make the choice between elegant, which Simula was for this problem, and efficient, which BCPL was. I want both. And that has been sort of one of my guiding lights. If you give people the choice of writing good code or fast code, there's something wrong. Good code should be fast. And I came away from Cambridge with that experience. Still thinking I was going to build operating systems and design computers.
So after graduating, did you look at a lot of places? You weren't interested in teaching? Was that true?
If anything, I was more convinced I didn't want to teach. I saw it as a trap for bright kids. And also I had developed this idea that there's something fundamentally wrong if the teacher's previous job is student. It's incestuous. There has to be some real world in there somewhere. And often there isn't for teachers and professors, and that weakens what is being taught. And it weakens the credibility of the teacher, so the effectiveness of transmission of data is also worse. So no, I really didn't want to do that. I looked at jobs in Denmark. Denmark is one of the nicest places on earth, and if I could have found a good job there, I would have gone back. But I noticed that I had made some kind of fundamental mistake, because at the time in Denmark the opinion was that if it was right and good, it was being done in Denmark. And since what I was doing wasn't done, it must be wrong somehow. Furthermore, for university jobs, the jobs went to people who were sitting around doing the usual thing for a couple of years till they could get a job, practicing teaching, doing fashionable stuff. And what I was doing was not fashionable in Denmark. And I got an offer to write some COBOL somewhere. That could have been a non-career very easily, didn't attract me. Got an offer to go and do something for some branch of the government, which seems to be counting submarines in the Sund outside Copenhagen. Didn't sound attractive at all. And then there was a connection between the lab at Bell Labs and the lab in Cambridge. And somebody had been around, and in the Eagle, where you went for a pint after a day's work, somebody, either Steve Bourne or Sandy Fraser, said, you know, if you need a job, give us a call. And they worked in the Computer Science Research Center at Bell Labs, so I did. And they said, yeah, you can come around. We can't promise to pay your fare, but come around, give a talk, let's talk. So I flew over to the States. I also arranged a couple of other interviews. But I came there and I was met by Sandy Fraser. Said, sit down. And I said, what do you mean? He said, sit down. So I sat down and said, you come at a bad time. We don't have any jobs. This is not how you want a job interview to start after you just crossed the Atlantic, you're seriously jet lagged, and your bank account is rather low. Anyway, so we didn't go to the Computer Science Research Center. We went to one of the more development-oriented places, and I gave my talk. And must have been a good talk, because they changed their minds, and I got put straight back on the car and did a full interview in the research center instead. And a week later I got an offer. So after that I worked there for 16 years, as long as AT&T still had Bell Labs.
Right. And is it fair to say that you started off doing work somewhat similar to your actual PhD distributed systems work?
Oh yes.
And then that led to some new things.
Yes, I was still, I thought, now I'm in an industrial research lab. We have many more people, we have many more resources. now I can actually build the system I was thinking about. And since we had Unix, and that was in the early days, all of Unix was there. It was a reasonable size, and there's people who knew everything about it, like Ken Thompson and several others. Dennis Ritchie was there to show how to use C, Brian Kernighan, Doug McElroy, Greg Chesson, lots of good people. So I decided I was going to take and build a system based on Unix by taking parts of the software and run them in different sort of unit modules, parts. And these, let's call them modules, should be able to run either on a shared program computer or over a network. We could afford a shared a multiprocessor. Didn't have one yet, but we could in principle. And soon we were going to get a network. We were all sharing a PDP 1170 at the time, but there was more of these, and it was obvious that soon it'll become feasible. So I set off trying to figure out how to separate the various services of the kernel into separate modules, and to think about how users could talk to each other through this kind of stuff. And after a while, I don't quite remember how long, probably a couple of months, I realized I was making the mistake that I had been very determined not to make. Because C, which was the language there, didn't have the facilities for saying which parts are separate, and didn't have the ability to say what is shared and what isn't. They all poke into memory and such. And furthermore, it's so low level that it's really hard to work with at that conceptual level. So I looked out for something better. I knew that to build the kind of distributed system I wanted, I needed a language that can deal with hardware. Do it well, do it efficiently, do it directly. C was a good example of that. I might have chosen Algol 68 if that had been available, but I soon realized that nobody was using that. It might be elegant, it might be beautiful, but this is not what there is. And I have Dennis Ritchie down the corridor and Brian Kernighan, so if I really want to know how to do it for real in C, I know where to go. But it couldn't do the high levels. It didn't have the notion of a module or an entity. Well, later we called them objects, right? And I knew Simula quite well. I had used it. I had been taught it by Christian Nygaard, which is the ultimate master of this game. He invented object-oriented programming. He invented inheritance, all of this kind of stuff. So I decided there was languages that could do that. Simula was probably the best. And there was languages that could do the low-level stuff, and C was obviously among the best. And so I wanted to put them together. And you couldn't put the low-level access into Simula. That was just too complicated, and the compiler was too expensive and too hard to port and too hard to target to hardware. So I put the abstraction mechanisms into C. And that's the fundamental idea of what was then C with classes and now C++. There's these two parts to it: the ability to manipulate hardware directly and the ability to abstract from it so that you don't have to work close to the hardware all the time.
It seems very simple now, but yes, it was a really good idea. And so it was a tool for your own project. But you sort of talked about other people looked over your shoulder, so to speak?
I talked to a lot of people, and I listened, I think, reasonably well. And so my sort of detailed ideas, not the fundamental, but the details ideas were sort of wrong. And I learned from people what they were trying to do, how they would like to do it, and a lot of stuff came into C++ from those applications. Thinking back, there was a couple of decisions I made very early on that was really important. I put in what is now known as function prototypes because I couldn't live without the ability to have a proper interface, to check your function arguments, to get conversions. The idea of square root of 2 not being a valid program was just, no, that can't happen. I was complaining a bit about that, about C, and Sandy Fraser says, why don't you just fix it? So I did. The other thing from my notes, my very first notes, was that you needed a constructor to construct an object, to acquire the resources necessary to function, to establish an invariant, to speak modern, and a destructor to clean up the mess when you're finished. And this is very, very early. It's the same kind of vintage as the function declarations. And there was one more thing that came in very early. It was very easy in the context of C, but it is where C++ breaks with many other languages. I really didn't want to have a distinction between the user-defined types that are created with new and live over on the free store, and the built-in types that you just declare and use and don't live over on the free store. So you had in Simula the distinction between what had pointer semantics, usually reference semantics, and what had value semantics. And I was quite willing to believe there was types that should have pointer semantics and types that should have value semantics, but I really wanted both, and I really, really wanted the value semantic types. I never could understand why an integer was something you could have a variable of, and a complex number, because I defined the complex number, was something you had to put on the free store and allocate with new. I mean, these are fundamentally the same thing. To quote Doug McElroy from about that time, there's nothing abstract about a complex number. It's as real as reals. So from very early on, the first weeks or month, you got functions with interface checking, you got classes with constructors and destructors, and direct support for value semantics. And that's sort of the rock bottom where things came from.
Yeah, as I was preparing for this interview, I was just thinking about the fact that you had done that so early. And back in the early 70s, there was a lot of discussion, research on extensible programming languages and abstract data types. And yet, people seem to somehow kind of get distracted by inheritance and the reference-oriented implementation models. And it seems that only you followed that other path and gave us the ability to define a type like the ones that were built in.
Yeah, it was on my list of things I didn't particularly like about Simula, and I talked to Christian about it, and he says, well, it's just the way it is. We had to put the user-defined types over there. And I said, that's not ideal. Similarly, but you couldn't build the garbage collector if you didn't have that. Similarly, I talked to Ole Johan Dahl, why don't you have multiple inheritance? Well, he said I couldn't build an efficient garbage collector if I had multiple inheritance. In fact, by modern standards, you couldn't build an efficient garbage collector at all. So when I was dealing with things at the lowest levels of the system, I wanted the efficiency, so I couldn't afford a garbage collector. So putting things over on the free store is something that is potentially expensive, but destructors take care of that, minimizing the cost. But I also really wanted the types I really think about. Complex numbers, points, sockets, matrices to be on the stack. because that's where I have the best control, the most automatic management of resources, the most efficient. It's the easy of use and efficient coming together again. I wanted them there, and that was something I actually more or less knew by the time I left Cambridge. Not in the sense that I was going to do it, but in the sense that it has bothered me that I couldn't do it. And then C, of course, has the value semantics at the base of itself, and that helped.
Yeah, but in a sense, it's as if you've taken out L60, which was stack-oriented, and then enriched it with the ability to use the off-stack, the heap storage, but in this controlled way. So it's very, very nice.
I could have done that. I wanted to do it to Argos 68, but decided that would be a really dumb idea because nobody else liked Argos 68. And if you wanted to do something practical, if you wanted to have an impact in the world, which I did, you have to do something that other people can understand.
Right, yeah. You have to sort of engage with the currents that are there.
Yeah.
So it sounds like at this point you're designing a language. You're also working on your original research project, but it's sometime in kind of the early '80s. It sounds like your focus really goes more to the language side.
Yes.
Is that right?
Yes. I had my first real user after 6 months. CV classes was a preprocessor, and it was fairly easy to get started. And it was aimed at writing some initial simulations that I needed to figure out how to design my stuff. And then other people started using it, and then when you have users, you have responsibilities, and you have to make sure that their projects succeed. And since I got more and more users, I spent more and more time making sure that my users were happy. And at that point, I was doing the documentation, the tutorial, the fighting bushfires, the teaching, the starting of projects, all of that. And I never got to build this system. Otherwise, we might have Unix clusters and Unix multi-cores about 85. But I got totally distracted, and for the next 10 years I was doing this combination of language design and support of users. I mean, I was the help desk for a long time.
Yeah, and I guess the level, many of the other systems there, Unix and C and so on, had a lot of those same kinds of documentation and so on, but that was typically spread over multiple people, so you were a one-man band
Yes.
So C++ sort of emerges as a name and as a new implementation and as a more sophisticated language around this time. First going to the outside world around 1985. Is that right?
We had educational releases and specific releases to people who asked to use it for educational purposes. So those people using it certainly in 84 and into 85. In October 85 we had a commercial release which was known as the brown bag release because it was so cheap. And because it has been so economical building it, I wrote 98% of everything there. Documentation, build procedures, testing, language, the works. So that was cheap because I was doing research, and actually what I was really doing was supporting users for doing interesting projects. And so from a corporate point of view, it was free. And the cost of getting an implementation for a university was $75, which was the cost of putting it on a Mac tape and shipping it physically.
Right. Okay. So essentially, that was free for academic use for all practical purposes.
Yeah.
And how about commercially? If
there was a rather large fee. I think it was $40,000. But then you got a source license, and you could do interesting things with it, and people did.
Were people running it only on the same instruction set that you were? Was that BCPL still? Or
no. Quite early on, I decided that running on a single machine was, well, suboptimal. The people I dealt with, the people who were my users or would like to be my users, or myself, didn't just use one machine. And so my C++ compiler, CFront, was a natural cross-compiler. And the way that tended to work is I would generate C for the target machine. So if you had a C compiler, we could hijack the C code generation and tool infrastructure and debuggers and such by generating C. But since C is not 100% portable, you have to figure out how to do this. And the way I did it, I wrote a little program that you run on your target machine. And it figures out what is machine dependent on that system. So if you have a Unix and a C, I can run this program and it'll tell me, it'll write a file that tells me what C is like on that machine. What is the size of an integer? What's the size of a pointer? Do you have signed or unsigned characters? So I get a little file which I mail back to the original, and you just plug it in. It was a plot plus X option that takes a file. And this changes the compiler's view of what it's generating for, from its own machine to the target machine. And so those really weird architectures, like the Craze, where it took a whole month, or the Univacs, where it took a whole month to port CFront. But most times we got it down to about 3 hours, which before shipping and packaging and large tools were actually pretty good.
Yeah. Did you, when this 1.0 release came out, did you actually include the binaries for a bunch of those ports, or how did that work?
I don't remember. Obviously, there was a binary for at least one machine on that tape, otherwise it would never have worked. But I don't remember. We did not generate 50 binary versions and put it on the tape. 50 is a random number, but I know the number of target architectures were more than 20, and we didn't do that.
Yeah, okay, makes sense. So perhaps without getting into every detail, it might make sense to talk a little bit about sort of how the language has evolved. You know, when you described the C with classes, it had inheritance but no virtual functions. It had this nice support for constructors and destructors and treating a user-defined object as essentially a first-class citizen. And now new things are happening in the language.
Yeah. When we changed from C with classes to C++, which was in the winter of 83, 84, I'd been working with operator overloading. I really needed to get the value semantics. I really needed assignments. And some of my friends needed operators. They actually needed AND and OR and XOR for some machine simulation kind of stuff. Not plus and minus, that came later. Actually, it was thrown in the same thing, but the demand was not for those. And the really interesting things were subscript and application, from which we get the current containers and the function objects. That came in then. The other thing that came in was virtual functions, which I knew from Simula, but I was totally incapable of convincing people they were useful. The attitude was, you want to call a function and you don't know which one it is? Haven't you analyzed your problem? And if you really need an interaction, why don't you just use a pointer to function? And well, I said you can't manage that at scale, and I can't teach it. And so we got class hierarchies a la Simula, but with multiple inheritance, because I thought I needed it. These days, everybody uses multiple inheritance. They use multiple inheritance of interfaces. Everybody who has a language that can specify an interface has multiple inheritance of interfaces. I hear Java 8 has finally gotten multiple inheritance of data also. It's not as useful as interfaces, but sometimes it's just the right thing. And I guess the main reason I'm mentioning it is that I've had so many years being told it was a design error. So it's interesting to see another major language adopting it in some form. And there's something important here.
References?
Once we've shipped release 1 and release 1.2, I actually got some time to think. I've been very busy for a few years, and I was thinking about error handling, and I was thinking about generic types. The other thing that you can find in the very first paper on C with classes is an explanation of why you need to parameterize things like vectors with types, because you don't really just want a vector of doubles and a vector of int, you want a vector of t. And that was in there very early, and I explained merely why you need it and how you could do it, claiming that macros would do the job. So I got the right problem and the wrong solution. Because again, macros is one of these solutions that works for one or two guys working closely together and knowing what they're doing. It does not scale. If you have many users, relying on macros creates hell. And so I needed something better. I knew I wanted it and I didn't know what it was. So I designed templates. And templates came with basically 3 fundamental design aims. I wanted it to be general. I had learned that I cannot imagine what people will want to do. And I'd suffered from languages that were designed to make sure that you could only do what the designer thought proper. I didn't want to design one of those languages. So generality was very important. The second thing was performance. I still would like to maintain what I had named as the zero overhead principle. That is, once you use an abstraction mechanism, you run as fast as the best hand-coded alternative in the basic language. And in particular, I really dislike the C array. The C array is the ideal abstraction of hardware as memory. You can't do better than that. It's a fixed size sequence of objects. That's all it is. It doesn't know how many elements there are in that sequence. It converts to a pointer with the slightest excuse, and the pointers convert to other kind of pointers with the slightest excuse, and you get bugs. It's one of the major sources of bugs. So I'd like to put arrays out of business. And I knew I would never be able to do that unless I could make an abstraction that could do a sequence of elements better than arrays, but at the same cost as arrays. And we're close to that with the current vector. So I needed something like that. Those are 2 things, generality and low-cost abstraction, zero overhead abstraction. And finally, of course, I wanted interfaces, good interfaces, like so I can get modularity. And I had to give up. Nobody knew how to get all 3. And I thought I had no choice but to meet the 2 first criteria. But the third criteria, decent interfaces, I think everybody else knew only how to do that if you either had macros, which are unmanageable, or have something that's less general, and is particular, have something that has a vector of functions, a jump table somewhere, which I couldn't afford if I wanted the performance of arrays for a vector abstraction. So that was a design problem that sort of defeated me at the time, and we've been working on it ever since, as you know. And Last week, they voted concepts out to national body vote. And so we should have a technical specification of concepts that solve that problem later this year. It should have been in 14, it will be in 15. The C++ Standards Committee has never lost a national body vote. As a matter of fact, we've never had a negative vote in a national body vote. We work very hard for consensus. So we should get it today, and you can download it and use it today in a branch of GCC. Andrew Sutton built that one. He used to be my postdoc. He's now a professor in Akron. And this is a design that many people took part in, including you, Paul. And a lot of inspiration came from Alex Stepanov. And some of the stuff came from me in trying to simplify the way it's expressed in a language as opposed to what should be expressed and how you could express it, which to a large extent mostly came from Alex.
Oh, well, that's really good news to hear. So this is a feature that's been 30 plus years in fruition, in gestation.
Yeah, I blew it in 81 or thereabouts, knowing I wanted it but couldn't do it right. I came a lot of the way in 88 when we got templates. Templates has been a huge success, but it has the weakness in how to specify interfaces, which gives really bad error messages, complex code and such. It's unnecessary. We tried again in 2002, but got distracted by people who wanted something that was truly object-oriented or just like Haskell. In both cases, you get these jump tables, these V-tables in place, and then you need heroic efforts to optimize them away. And these heroic efforts don't tend to scale. That is, you can get really good performance of a sort of a Pobble-sized program. Fits in one column in a Pobble paper. But if you if you're doing it in industrial scale software, the optimizations don't get good enough, and you get costs as if you were going through the interface to a abstract class or something, which we can't afford. Not if you want to compete with arrays.
Right. Yeah, I was thinking as you were mentioning that principle of the no overhead performance. That really, you can trace that back to the original Fortran project. John Backus had a goal that he wanted a language that scientists and engineers could express their problems in, but that the professional assembly language programmers of the time could not do better hand optimization. And he was actually able to achieve that. So by a balance of not overly complex language structures and then a very good compiler.
Yeah, I mean, this idea that things has to be affordable is really, really important. There are lots of areas where you can waste a lot of computing power. I mean, our cell phones has 1,000 times the performance on the PDP-11 that I started the CV classes on. And similarly with the little VAX machines that I completed the job on for the commercial thing, it's 1,000 times and more memory than that. And people can afford to throw away 95% of that or 99% of that and do a lot of things that they want. So please don't get me wrong, I'm not saying everything should be efficient, but some things have to. Fortran lives because there are applications that takes the biggest computers on the earth months to do. And C++ survives for this kind of stuff because there are things like the video cards and the graphics, the networking software, the signal processing and such. All of this kind of stuff that's at the bottom of every system has to be efficient. And if you can run twice as fast in those areas, well, you need half the number of computers. If you look at Google or Facebook and their server farms, if you use a language that's half the raw performance, you need twice as many server farms. This can be measured very easily. You just count 1, 2, 3. cooling, twice the maintenance, twice the monitoring, twice everything. I've talked to people concrete about what they can do on a machine, and they really want the latest optimizations in C++ because they really need that extra factor of 2 or 4 or 10 that you get compared to some other languages, or 50 for that matter.
Right. We sort of, in some sense here, this has been very interesting. We've kind of jumped ahead of the story that you were telling us earlier. These features were some of the last things, the templates and exceptions that you had been thinking of, but that around that time you were also starting to think that you needed to standardize the language. Could you tell us a little bit about that?
Sure. Yeah, this is typical. We drifted away from sort of the history and into the design issues.
That's fine, but
yeah. No. I'm just thinking back about what we were saying. No, I did not decide that we needed to standardize. A couple of guys, Dmitry Lenkov from HP and somebody from IBM, I don't recall the name right now, came to my office one day and said that I wanted to have ANSI standardization of C++. And I sort of tried to explain that this was a dumb idea and that the language wasn't finished and I needed more time, and they explained to me that you couldn't have a language in major industrial use where you could lose the design implementation team because you got run over by a bus. Very nice, polite explanation. So I still talked about how I needed more time, and they twisted my arm a bit more, and in the end I went, ow, yes, I'll do it, we'll do it next year. And we agreed on next year. And so the first meeting happened in December, because, well, that wasn't next year, but it was close enough and anyway, so that's how we started. No, I did not have the very correct idea that we needed standardization. I was too busy doing my own stuff. Now, ANSI and later ISO standardization is a huge pain in the neck with lots and lots of people involved, lots of people working very hard, very often with no clear idea of where the language should be going in the future. Very often with the idea that if we can slow down progress and change, we can get something that's good and stable, and let somebody else do the innovative stuff, and others who wants to turn it into the latest fashion. I mean, for all of the 90s, people wanted to turn C++ into a truly object-oriented language by jettisoning the C idea, except for the part of the committee that really couldn't care too much about the object-oriented stuff and would rather it was closer to C. So having direction in a standards committee is really hard. On the other hand, the guys were fundamentally right. You needed some organization that keeps the language stable and evolving. And that's very hard to do. I think things would have worked much better if we had had some resources so that there could be a design or evolution group that worked full-time on where the language should be going, and then the committee as large would deal with polishing and checking and compatibility issues. But that's not the way it is. There is a group in the committee that deals mostly with future stuff, and there's others that deals more with sort of everyday problems, and there's a tension there, but there's no resources for doing a serious experiment, for instance. We try and improve the process. We now have study groups that run in parallel, and we have more internal groups, but now we have communication problems between the different groups and such. It's very, very hard. So you need a central organization, you need more than one guy or a couple of guys to run something this big, but organizing that is really difficult.
Well, you've stayed all through that process as the principal designer of the language, and yet other people have been contributing ideas and features. What does that sort of feel like, just from your point of view? Was it sort of having your daughter get up and get married, or
No, it's nice when people improve things. It's really painful when people try and take the language into a direction I really disagree with, and then you have to stop. And it's really painful when I am really certain about which way we should go, and people say, oh, we can't do that, or we should make it more elaborate and more complicated, and we really must follow this fashion, not what you are saying. So it's hard to get things through. Of course, sometimes they were right, and I shouldn't go the direction I would have gone. I hope I would have discovered in time, and it would not have been set in concrete. But certainly the breaks have worked at times, and sometimes we've gotten things that probably shouldn't have happened because there's a committee and you can't be everywhere. But it's very difficult. It's something that's underestimated. I really understand why most language designers don't do this, or why no language designers do this. Other languages have committees that are disjoint from the original designer or designers. Other languages have dictators for life or something like that. Going through the standard process has its strengths and weaknesses, and it's certainly very painful if you're the language designer, but possibly necessary.
And yet, from what you've said in the latest version of your language book, you seem to be pleased about where the language has gone.
C++11 and C++14 is just a much better tool. And one of the reasons actually is that I succeeded to some extent with my sort of the current push is to make simple things simple. I was part of the people who did the for loop, the range for loop, like in many other languages. Auto, which is like var or let in some other languages, is something I implemented in 83, 84. And was forced to take out again, partly for C compatibility reasons and partly because nobody could understand what it was for. Similarly, we might get coroutines now, finally, which again was something I was doing in the very early days but haven't been able to get through. That's future. But some of the things people are most excited about C++11 actually is not the advanced features. It's some of the simplifying features so that they can write less code or repeat themselves less often, fewer opportunities to make mistakes. I'm not a fan of the current trend of trying to absolutely minimize the amount of typing you have to do, partly because then you have to know so much and there's no clue left in the code about what it means, and partly because we read code much more than we write it. But certainly C++ has become too verbose. One of the things about concepts is that it actually simplifies the syntax of writing simple templates. So instead of writing template type name void of sort I of I1, IF, I2 and all of this, you write void sortable ref C. It looks just like the function declarations we were used to in 82 or thereabouts. And basically concepts can handle the old view of a concept being the type of a type, and it generalizes to saying that there should be a set of types and values that should meet a set of criteria. So you can say that merge takes 3 types that should be mergeable, meaning that there should be an input, 2 input streams, there should be an output streams, and the relationship between the input and output streams has to be just right. We can express that with simply saying mergeable I, O, something like that. Oh, and the criteria.
Right.
So again,
Yeah.
I have this design idea that simple things should be simple, and complicated things, well, they'll have to be a little bit more complicated, and I hate making anything impossible.
Right, but in those examples with C++ 11 and 14, it's as if there's a sort of almost a scripting language style of programming has become possible. So it's a new paradigm in a sense.
Could be. It's still strongly typed. As a matter of fact, the code I write today are more strongly typed than it used to. Furthermore, it's statically strongly typed, not this scripting interpretation. And one of the things we are doing with concepts is we are going away from the duck typing model of templates, which is what most of the scripting languages are doing, into an interface-based model of computation, which is what the rest of C++ is. And the scripting languages, by and large, are not.
Yeah, scripting is not the best word. Maybe say casual programming. You know,
yeah.
It's this compactness.
Yeah.
That's very nice. By the way, speaking of concepts, you alluded to Alex Stepanov and STL earlier in the talk, but it might be a good time for you to just say a little bit about how you got to know him and what that has led to.
Yes. Alex worked at some part of AT&T for a while, and before that he had been at GE, and he's moved around a lot. And I remember discussing things with him pre-STL when he was at AT&T, and he was trying to convince me to do things the way they're done in Ada, because that was the language he was using at the time to express his ideas in. And I learned a lot from him, but I was not going to go that way. In particular, I was not going to have any statements for instantiating generic types, and I was not going to put in the restrictions for so that you couldn't have conversions. I mean, to this day, Alex and I disagree with what you do with mixed mode arithmetic. I really like to be able to multiply a double with an integer, and in generic context that creates some complexity. But I also learned something about what could be done from Alex, and the importance of being able to inline everything. Type information mustn't get lost. This completely plays into my zero overhead bias in design. And then Alex went away, and I implemented the first version of templates. And then something came back via Andrew Koenig, which was the STL. And to be honest, I thought it looked really ugly. And it certainly looked completely wrong. Like everybody else at the time, I had gotten this idea that things had to be object-oriented in the container world, and you had to have a hierarchy of containers, and you had to have a hierarchy of iterators, and I was working like that, and of course STL is totally different. I mean, the STL is based on the notion of concepts. There just wasn't any language support for it, and it's based on generic programming, and it meets the zero overhead principle because the code generated from it is really, really beautiful from a machine point of view. Furthermore, it was not just a container library, it was a container and algorithms library. Or I guess from Alex's point of view, it was an algorithm library that also had some containers. And I looked at that for a couple of days, not being very enamored by it, and Andy was pushing that this really works. And it turns out that I had over the years built up a set of criteria for what a good container library should look like. I actually had a list sitting somewhere with, I think, 11 points. You can find it in my third edition of the C++ programming language. And checking Alex's design against my list, I realized that apart from everything else about the STL, it met 10 out of 11 of my criteria. I may get the number slightly wrong. Maybe it was 12 out of 13, something like that. But certainly there was only one thing left. And the one thing was having facilities common to all containers, things in common for all iterators. That way you could get debugging or serialization or something. Anything but that it did, and it did very well. And so I think, well, yeah, it looks odd, but you know, it meets all the criteria and nothing else does. Actually, all but one of the criteria is nothing else done. I've been looking for years. I haven't found something like this. And then it does all of this neat stuff with algorithms. And so, yeah, this is good. The chances of the standards committee accepting it is, of course, very low, but, you know, it's so good it's worth trying. So we did a few things with the standards committee, including bringing Alex in. And Alex is an absolutely first-rate rabble-rouser. And he got those guys excited in a way I've seen nobody else being able to do. And I kept plugging, Andy kept plugging, and after a couple of years we finally got it in. And that was very, very difficult. You had to convince a lot of people with different backgrounds. There was a couple of critical things like Beeman Dawes, who is one of the founders of Boost. In the middle of, I think, the meeting after the one where Alex had explained things, when people were being somewhat rude about the STL and its complexity and its difficulty and its ugliness, he spoke up and says, you know, I thought that too. But since the last meeting, I just thought I would try and see what it was, and I implemented about 1/10 of it. And you know, you're wrong. It's not that complicated. It's relatively easy to do, and it's cleaner than what we're doing. That was very important. Again, this thing about the standards committee, there's lots of people. Sometimes they really help. Sometimes they get in the way. But in this particular case, Beeman's contribution was essential. Another reason why it was very difficult to get a library like the STL in was that everybody by then had their own object-oriented container hierarchy. And at one point, Texas Instrument was going to propose their very nice object-oriented container library. And they were going to do it right after lunch. And the rumor spread in the committee over lunch that they were going to do this. And after lunch, I think we had 5 more organizations saying that if we are even going to discuss this proposal, you're going to discuss our corporate hierarchy also. And these also guys are people like GNU and IBM and Microsoft and Borland. So these are not lightweights. And it was obvious that it would run into impossible opposition. And the fact that the STL was so different and the fact that it had the algorithms were probably crucial to get people to look at it. It was a beautiful piece of work, it still is.
And so things kind of fell into place with STL eventually. I mean, after these things you described, and from that point on, it kind of became accepted. But the concepts issue was something that sort of, in some sense, it really created a new demand for solving that problem, because now
Yes.
you have this rich set of algorithms that you'd like to describe.
Yes, there's a huge pressure for concept that was building up from 2 sources. One was simply the bad error messages, and 2, from my perspective, was that people got really enamored with the doc typing. Templates provides compile time doc typing, and so we get a lot of compile time work and a lot of doc typing where we don't quite know what's going on, and where the implementations of the templates sort of shines through because there's no interface and you have to know it. And so we got some horrendously complicated code that does amazing things, but people have trouble understanding it and where the limits are. And so my view is we need concepts for the traditional generic programming and for some of the template metaprogramming to introduce proper interfaces. And then we'll see what's left after that. Expression templates cannot be done well with concepts because you're simply manipulating syntactic structures. They don't have semantic meaning till later, so that's a problem that's left. The other thing that happens with templates was that people realized that templates couldn't just be used to generate new types. They could be used to generate values. And a lot of template metaprogramming is programming that generates values like 2 or 32 or 99 or something like that. And some of the weirdest code is like that. And essentially all of that can now be done with what's known as context functions. That is, functions that can be computed at compile time, which is a complementary approach that Gabi Reyes and I did, realizing that there was a major need for compile time computation, both from the embedded systems programming and also some of the stuff that we saw done with templates. And computing a value, you just use a function. I mean, we know how to do that. That should be just that. And people in the embedded systems programming world tended to use macros. And now you get to typeless programming. And people in the template world use templates, so now they get duck typing. And we really wanted ordinary functions where you give arguments of a given set of possible types and you generate results in the appropriate thing. And that's all. It should be like we're back learning our first function. And we're getting there. Constexpa is in C++ 11, it's heavily used. 14 it does it a little bit more general. That is, you can now have a loop inside a Constexpa function. That means the fundamental rule of a Constexpa function is that it can be done at compile time. It means it cannot have any side effects because the rest of the world hasn't been created yet. So obviously they must be side effect free. That means they are pure functions. It also means that any state that exists only during the execution, and you get some really nice stuff out of that. So there's actually 2 attempts to limit the weird forms of template metaprogramming. Limited template metaprogramming to where it's actually you want metaprogramming. And the one is to take the generic code out with concepts, and the other one is to get the compile time computation done with functions. And of course, Constexpa functions can be templates that can take concepts as argument types, so it all fits together. Similarly, the function objects that we've been using for years with templates and with the STL, I mean, function objects goes back to 83, when I allowed the overloading of the application operator, and we've been using them ever since. There's versions of them that early. They become essential with the STL, which is the efficient way of parameterizing with an operation. And then people come with lambdas, and you can define a function object right in the place. So a function object in C++ is something with an application operator. Lambda is something that generates a function object in place and invokes it when necessary. So it's a shorthand notation for function objects that we'd had all the time, and they run as fast as function objects, possibly even faster if you do trickery with stack frames.
So, right, C++ now it supports pretty rich functional programming and abstract data types, object-oriented programming. It's all those languages that you studied in the 70s are here and more, and in one framework.
In one framework, that's important. I mean, that was why I emphasized that lambda is really a function object, and function objects have been there since before day one for C++. So it does fit together. There's a lot of barnacles there, which sort of is complicating writing code, but there is an inherent logic there. And I was not deeply into functional programming in the 80s, so this is relatively new. I knew the abstract data types, I knew the class hierarchies, and I knew the close to the machine programming. Functional programming is a set of ideas that has grown over the years, some of them coming out of the Lisp world, and now we have some of the aspects in C++. But it ties together with what's been there for a long time.
Right. Well, that reminds me of one of my other questions. In your Hoppel paper, the third Hoppel conference,
yeah.
You mentioned sort of three key properties of C++, and you sort of sketch how you might be able to build a kind of a simpler language that would have the spirit of C++. Have you done any more thinking?
Yeah, I've done a lot of thinking about this. I think the key statement in that conclusion section of the Hoppel 3 paper is, I think we can build a language with the expressive power of C++ and the ability to deal with hardware the way C++ does. That's a tenth of the size, measured any way you like for size, and without loss of performance. And I think that can be done. I have worked more on these ideas. If you look at the move semantics, coming mostly from Howard Hinnan, but following trends and dirty trickery that we used for years to get effects like that, but they didn't scale till Howard's contribution. We can now build basically a closed system where we do not leak resources. So I talk about resource safety. People talk about memory safety. That is a relatively uninteresting thing. You can cripple a system much faster by leaking file handles than any other leak I can think of, including memory. So I want, when I talk about resource safety, which is something I want, I'm thinking about file handles, thread handles, locks, sockets, the works. And I think we can do that now. Garbage collection gives us one thing which is a problem for the kind of world I have, and that is if you take a pointer to something that's local and then store it and wait for the stack frame to go away, you have a major problem. And how to avoid that, I'm not quite sure of. There is several ways, but I haven't decided which is simple, elegant, efficient, teachable enough. But yes, I still think you can build a C++-like language that's much smaller than what we're dealing with now. I would not throw away C, but I might throw away some of the syntax of C. C is a model of how to deal with things. It has objects, it has pointers, and that's very important. It maps to the memory, and you need that for a C++-like language.
Well, let's see, there were some other things that I wanted, hopefully, to have time to talk to. It looks like we do have a little bit more time, if you do. We sort of left, in some sense, your own personal career, and we focused more on the language. Maybe we could kind of look back
Sure.
and say that a dozen or so years ago, AT&T ceased to be the right place to be, and you actually made an interesting career transition there.
Yes. So Bell Labs, AT&T Bell Labs, at the height of its powers, and I think the 80s and 90s, was just a unique place in the world. There was no place like it. In the Computer Science Research Center, we had between sort of 30 and 60 people during that period, and many of them are still my friends. I mean, extraordinary number became famous in one way or other. IEEE fellows, ACM fellows, member of the National Academy and things like that. And we're just doing sort of interesting work at the time. And the environment that made that possible, Bell Labs, the philosophy that you could let smart people work on things they thought interesting rather than having a command economy, and that you had a management structure that kept that from going out of control. It puts a lot of emphasis on really good department heads, really good directors, so that you actually get something out of a system like this. And the idea that you have a mixed portfolio of research, so that something comes along every year or so, but that doesn't mean that you can only work on things that will come to fruition next year. A lot of us were working on things that takes 5 or 10 years to come out. But every year, every department delivered something of interest. And managing that was difficult. The environment was really nice. A lot of the people were nice people. A lot of the people are still my friends. Of course, there was people with enormous egos. There's no shortage of enormous egos in the computer industry. But many people had no need to have a huge ego or be rude. And they were some of the nicest people I've met. That was a good time, and that was a good time. I brought up my children in near Murray Hill in New Jersey. People have the strangest views of New Jersey. If you try and land there in a plane, you can't find it for the trees. That is not the image that people usually have, but it's a good place to bring up children. It was a good place to work. Then Wall Street got an idea that vertically integrated companies couldn't possibly work. And so you need to chop all the pieces, and they also had the idea that everything that can be invented has been invented, so you don't need research or advanced development organizations, so you have to cut that. Both theories are wrong, but it hurt Bell Labs enormously, and it became a far less interesting place to work. First, the Bell system was broken up, and then AT&T and Lucent split ways. The idea being that some people built the switches and the other people built the software for the switches, and how that makes sense to separate it there, I don't understand, especially since my background is to working in exactly that interface. Anyway, then we had some good years at AT&T Labs. I was in Florham Park, just on the other side of the Great Swamp from Murray Hill. And then we got hit by another set of cutbacks forced by Wall Street that didn't have much foresight about technology and no tolerance to delays from research, and was misguided by false information given by WorldCom. They got fined later for giving bad information, but it hurt the labs badly. We lost 40% of our PhDs in one massacre. I was a department head at the time, and they laid off 2 of my people without telling me. Possibly because they knew that I would have hit the ceiling very fast if they had told me. So after that, I was open to new challenges. I mean, I wasn't laid off, and I had a nice corner office and all of that, but the oxygen has been sucked out of the air. I noticed that the people left behind was on average less interesting than the people that left. The people that left were the troublemakers, the people that would pin down an executive in the corridor and tell him he was all wrong. Those guys left, and those were the interesting people to talk to. And then it so happened that our youngest son had just gone to university and was settled in there, and so the kids have gone to university and had a lot of fun, so why shouldn't I? So when some of my friends suggested I should go and become a professor, sure, I'll try that. I mean, now I've been in industry for 24 years, I actually have something to tell the students, as opposed to when I just came out from school. And so it happens they were working on some interesting problem at Texas A&M University, and this was a department that really wanted to improve, and we have gone sort of 20 spots up in the rankings since I joined. So we did do something good, and we rejigged the whole curriculum, and I tried to do academic research, I tried to teach freshmen, I tried to teach graduates, I tried to supervise PhDs, all of this good stuff. This was interesting. But after 10, 11 years, it was beginning to go a bit stale. And also I have some problems with academic research. It has a tendency of drifting away from real problems. You abstract from a real problem, then you abstract from the abstraction, then you solve the abstraction of the abstraction of the abstraction, which may or may not relate to the original problem. And so I had some problems there. Some of the stuff I thought was really interesting to work on was unpublishable. I once wrote a paper on how to do abstract syntax trees, 30 times better than GCC. And the paper was rejected on two reasons. Three reasons. The first was that we had misunderstood C++. This was me and Gabby Reyes, who was the French representative on the Standards Committee and one of the best people on the standard. Also, he was the shipping manager for GCC. They also claimed it had been done in GCC. I mean, this is total bogus. And then when we complained, the thing came back and says, oh, that's engineering, we're computer scientists. If we had been in engineering for cars and come up with a 32 times improvement of one of the key components of the gadget, we'd have been heroes. Here, it took several more attempts to get the stuff published. And by the way, it's now in use in various of these compilers. But these kinds of things were grating, these things are discouraging. And in particular, it makes it hard to bring up students well. Because if you want to graduate as a PhD, you need to have publications. And de facto, that means you have to follow fashion. And, well, following fashion is not that fun. So I was beginning to think it's time to get back to industry, back to the kind of problems that I know and like, and get them in the real form rather than the distilled form and cleaned up form you get in academia. So again, I was sort of open to suggestions, and it so happens that every year since the 80s, I've been going around giving talks in industry and academia and such. Basically, I exchange a talk about what I'm doing for an explanation of what their problems are. And that's one way of making sure that when you work on a design, when you work on the evolution of something, it actually has a direction. And so I went and gave a talk at Morgan Stanley in New York City. And after my talk, the sort of not unusual suggestions started coming that maybe I'd like to go and work there. And my answer was, of course not. I mean, you're a bank. The kind of stuff I'm doing is not what interests you. And this is fine. We like this kind of stuff. And they point out some of the things I'm doing that they're interested in. And I said, oh, my time horizon is all wrong for a bank. I mean, some of the things I really would like to do takes at least 5 years. Oh, no problem. So we went through the song and dance, and eventually they wore down my usual defenses. And then they had one secret weapon that they didn't even know they had. Of all the organizations that had the properties that I could work for, they were the only one who lived within 20 minutes of my grandchildren. And so I'm semi-logical about this kind of stuff. I have a set of criteria, they met them. Other people meet those criteria, but they were in the right place. So
Right.
I'm now sitting in my apartment, which is halfway between my grandchildren and my work.
Well, that's a pretty nice place to be.
Yes.
Well, that's a very interesting story. So, at Morgan Stanley, you are designing future versions of C++, thinking about other programming languages, and what else?
I spent a lot of time looking at problems in the bank. A lot of them to do with networking. A lot of them to do how to express interesting coding problems. A lot of them has to do with performance. A lot of what I'm doing is fairly close to the hardware, but not everything. So in some sense, from that perspective, it's the same as ever. They have different kinds of reliability problems. I'm always interested in reliability of dependency. And they do have the interesting thing that you can't lose a penny. The answers has to be correct to the last penny. If you're doing a nice video system, if you lose a frame, it doesn't matter too much. Even if you're doing a fuel injection, you can't lose a cycle, but if you're ever so slightly off for a single squirt, the engine will still keep running and you can correct it for the next circle. With money, you can't do that. It's against the law. You have to get it right every time, not just on average. So there are interesting constraints on the problem, but basically performance, reliability, correctness, same kind of stuff. And so I'm now closer to reality and I can do better language design. I'm still part of the standards committee, and I'm also a professor at Columbia now, so tomorrow I'll go and give my lecture, and so I'm leaving academia means I'm actually a professor twice over, because they wouldn't let me leave Texas A&M either. But most of my work is in the bank and working with the code bases that we have there, and that informs my work on the evolution of C++ and my thoughts about what can be done better.
Well, you mentioned the challenges of being in academia, but do you have some advice for a future grad student who would like to impact the world of programming language design?
Oh dear. There is a lot of people who come with the firm idea they want to build a new language, or they want to build a new game, or they want to build a new operating system. And what is lacking in most cases is an understanding of what's the problem. That is, C++ succeeded, not so much because I made a beautiful design, but because I was really lucky of having identified a problem that a lot of people were about to get, namely handling complexity with larger memories and faster processors. We were then starting to write more complex problems, and I was trying to deal with complexity. But complexity under the constraint of performance, which was what people didn't get. So that's the fundamental problem that I decided to attack, and I was lucky I wasn't alone, and my design was good enough for a lot of people. So when people want to look for a problem, I think first of all they shouldn't look for a project just to change the world right away. They should try and understand the set of problems and then come up with solutions. And you can do very particular solutions trying to meet the deadline for the next quarter. And that's probably the best way of getting promoted. And soon you'll become a manager and you'll never do something really useful again. Or you can start learning from the experience, generalizing the problem and seeing, is there a solution that can help a broader spectrum or a larger group of people, larger set of problems, larger time scale. And so focus on the problem and use the initial projects and your knowledge from university to come up with a solution there. I think all of our theory and all of our courses helps us solve a problem. But we have to find the problem first that's worth solving and find the constraints on the solution to the problem. After that, we have pretty good ways of engineering a solution.
Okay, thank you. That's very interesting. One sort of final area I'd like to just touch bases with is the Computer History Museum. Was you donated, or you orchestrated, maybe is perhaps the best word, the donation of the C-front source code to the Computer History Museum. We're really grateful for that. What are your ideas for how the Computer Museum can help both researchers and students, or educators? Any thoughts you have on that would be?
First of all, I should point out that getting C-front into the archives was your idea. And I thought it was a splendid idea, and thank you. I just collected some of the pictures and the source code and the manuals and such. So this was good. I think that students are, by and large, ahistorical. They have not been taught history, they don't understand history, and they think that history has nothing to teach them. Everything was invented yesterday, and everything is the latest fad. And I think that that is most unfortunate, and I think the schools are encouraging this. There's a lot of schools that look only at, if they want to be engineers, they look only at their science and engineering scores, forcing them to not take, say, history in high school, not to take a liberal arts education in university, but just do the thing that's required. And there is a lot of emphasis in the press and elsewhere about the best career being the one that gives you the greatest amount of money soonest. And that is not a long-term motivator. The people that come through this successfully are often not very nice people. They have spent all of their childhood, youth, early adulthood in a very narrow area and focused on the career to the exclusion of everything else. That's not good. And I think people should know more general history, and they should be better at communicating, which probably the best way of getting to be better at communicating is to read a lot and to listen a lot to other people. And I think the Computer History Museum can help motivate by actually showing some of the things that were done in the past, and especially if they focus a bit more about why things were done. I went through the Computer History Museum some time ago, and I went through some rooms. And here is model X of computer from factory Y. Here's model Z of a computer from there. And sort of, it looks like one washing machine after another. And that very soon gets stale. Yes, I was excited. I realized I programmed this one. Oh, that was a fun one. Oh, I couldn't get that one to work. So if you can go through that, there is something there. But for most people, it's just, there's not something that motivates them. It doesn't tell why that thing was being built. What are the kind of problems it was used for? Showing just hardware, I think, is uninteresting. And there's a tendency of focusing on hardware because you can see it, you can knock on it, it's pretty pictures. But a computer without software is sort of a kind of a boat anchor, right? And so more emphasis on software, not just languages, but what did that computer do for a living? How did people interact with that computer? What kind of problems was it used to solve? What kind of tools did people use, in addition to the hardware, to provide those solutions? I think a greater emphasis on that would be helpful. I may simply be behind the times, and the Computer History Museum may be looking far more like what I'm describing than it did when I went through a couple of years ago. But I don't want to see another dishwasher-like piece of hardware out of context. And I think as a museum, you have to collect artifacts, and compilers, databases, application programs should be part of those artifacts, since there are many pieces of software for each piece of hardware. There should be more software in the museum than hardware if you want to reflect reality. But once you present it, you have a challenge, because software you can't see, you can't feel, you can't knock on it. And so I think the context of the computer, the use of the computer, the problems that was to be solved by the computer is probably one way of addressing that.
Oh, that's very interesting. I think you'll be pleased. Well, the Revolution exhibit is certainly better at giving context than the original visible storage area. I'm not sure which one you saw. But they're working on a major software exhibit. They still need some more funding for that, and it's trying to show maybe a dozen applications and systems in context. You know, here's the problem to be solved. So when that's available, hopefully you'll get a chance to come out and see that.
Sure.
I just need to correct the record. It was really Alex Stepanov who inspired me to collect not only C++, but a lot of the other source code.
Alex is at the root of many interesting things. I didn't know he had prodded you in that direction. Yeah, but I certainly know it was you who prodded me so that I delivered the stuff.
Right.
Thanks.
And I greatly appreciate it. Well, I think that kind of wraps up most of the things that I was hoping that we could talk about today. Is there anything you'd like to close?
There's something behind you.
Paul, can you hear me?
Yes.
Okay, I'm going to ask one question, which you already covered. It's fascinating that David Wheeler, Maurice Wilkes, and you are all fellows.
Yeah.
Now. And could you just talk and give us a quick statement about how, it sounds like you thought that was pretty cool. Can you just tell us, a little bit, think about speaking to the audience at the Fellows and how cool you think it is that you are part of a family line at this point.
I mentioned earlier history and the importance of history, and I don't think history is something dead. It's part of our world, it's part of the way we understand the world. And so for that reason, I have known about the Computer History Museum and its fellows for many years, because it's one of the things I've been looking at. I've been there physically, I've been there on the web, and I find it's really cool. I mean, not only being a fellow there, so having been part of all of this and being recognized to be part of all of this is very, very exciting for me, and I'm very honored. But I'm probably the first third generation fellow. That is, my advisor was a fellow, and his advisor was a fellow. We're still a young field, so hopefully there will be many more third generations eventually. But that struck me as interesting, and I actually went and I read a fair number of these short stories that goes with the fellows, and in many cases I was sort of wondering what else is there. I'm very slow at watch movies, because they move fairly slowly, and I'm busy or I'm tired or something. So if there had been some transcripts of their presentations that was linked from the bios, that would have been really useful for me. And not everybody can do what I do. Is for some of them I can sort of remember them, and they're real, and the biography is something that prods memory, and that's nice. But for others a little bit more information. The videos of things like this will help. Transcripts, if available, will help people that are busy.
That's great. That's all I have. Paul, how about you?
And of course, I'm very honored. I think I said that, but actually, just make sure.
Why don't you start again? Just give us one last little quote. I'm
sure.
Very honored.
Yeah, and of course, if I didn't say it already, I am very honored, and this is very important to me. Thank you.